Hello. In today's lesson, we're going to go over how to calculate cell potential under standard conditions. So in the previous lecture, we went over a galvanic cell, which is an apparatus that makes use of a spontaneous redox reaction to generate electricity, to move electrons around. And so we need to know what is the voltage for that. Just like when you buy a battery, galvanic cell is basically a battery. It tells you the voltage, which is the electrical potential difference between the anode and the cathode. And we'll go over that in a few minutes as well. So to calculate the cell potential under standard conditions, which we call E standard cell, and standard condition means you have both reactants and products present. If they're solids, they are pure. If they're liquids, they're pure. If they're gases, their partial pressure is 1 atmosphere. If they're aqueous, their concentrations are 1 molar. But they both are present, and temperature is 25 degrees Celsius. So that hollow circle means standard states. So to calculate E cell under standard states, we take the potential for the reduction half reaction, which is what happens at the cathode, plus the potential for the oxidation half reaction, which is what happens at the anode. I like this formula better, but some books, I think including your book, uses this formula, which says E reduction cathode minus E reduction anode. So it uses reduction potential for both of them. But I think if you use this one, it makes more sense, and you'll see in a few minutes why that is. So in order to get those values, well, we go to the reduction potential table. Remember when we went over oxidation reduction reactions and strength of oxidizing agent and reducing agent, we use this table. Well, this table quantifies the reduction in terms of reduction potential. And reduction is the tendency to want to grab electrons. So for example, the tendency of fluorine gas to want to grab electrons and become fluoride ion is plus 2.87 volts. Or for chlorine, it's plus 1.37 volts. Now, these potentials are relative. It's not absolute. So it's just like height, which is relative. So sea level is our reference point and it's 0. Anything above sea level has positive height, like Pasadena is, for example, 400 feet above sea level. Anything below sea level has negative height, like Death Valley is 200 feet below sea level. And so for this table, we set the tendency of hydrogen ion to want to grab electrons under standard states to be equal to 0, and then we compare the tendency of everything else relative to hydrogen. So when we say that the tendency of copper ion to want to grab electrons under standard states is plus 0.337, that's relative to hydrogen. So relative to hydrogen, copper 2 ion wants to grab electrons more eagerly. On the other hand, zinc ion is negative 0.762, which means compared to hydrogen ion, zinc ion in solution wants to grab electrons less. It's kind of like the Death Valley, it's below sea level, where the copper 2 ion is above sea level, it's like Pasadena. So the standard hydrogen electrode is what we compare everything else to. And the standard hydrogen electrode is simply this half cell. SHE stands for standard hydrogen electrode. So you have hydrogen in solution at a concentration of 1 molar. Above it you have hydrogen gas, gaseous hydrogen, at a partial pressure of 1 atmosphere. Since since hydrogen is a non-metal and it doesn't conduct electricity, you have to provide a highway through which electrons can move, so we use a platinum electrode. So in all exercises you do, whenever you see a platinum electrode or graphite electrode, is because you used something that in the oxidized or reduced form could not conduct electricity, was not a solid that could conduct electricity. So therefore, a platinum or a graphite electrode is used instead, which doesn't react with anything, it just provides a highway through which electrons can move. So this is your standard hydrogen electrode or half cell. And then we connect other half cells to this under standard conditions. And we put a voltmeter there to measure the voltage, the electrical potential difference. So for example, if I were to put copper 2 copper half cell here and hook it up to this one with a voltmeter, the voltmeter would read positive 0.337. The electrons would be moving from the hydrogen standard electrode toward the copper 2 standard electrode. And it would read plus 0.37 volts. Now what does that mean, plus 0.337 volts, which is written on the table over here? So 1 volt is defined as 1 joule per coulomb. So volt is a measure of electrical potential difference, which is similar to gravitational potential difference or height difference. And its units are in terms of joules per coulomb. Coulomb is you learned that in Chem 1A, it's the SI unit for charge. So, for example, electrons, their charge in terms of coulombs is very, very small, like 10 to the power minus 19. Remember Robert Millikan discovered the charge of electron. We call it -1 because of the sake of simplicity, because proton has the same exact charge as electron, but opposite. But in terms of coulombs, its charge is very, very small. And 1 mole of electron, 6.02 times 10 to the 23 electrons, carries 96,500 coulombs of charge. So 1 mole of electrons carries 96,500 coulombs of charge, and that's called Faraday's constant. So that way you can go from moles of electrons to charge and vice versa. So anyways, volt is defined as joules per coulomb. So if you have an electrical potential difference, like if you have a battery that's 1.5 volt, that means for every coulomb of charge that goes from the anode to the cathode, 1.5 joules of energy will be released. If the battery was a 9 volt battery, that means that for every coulomb of charge that go from the negative end of the battery to the positive, the anode to the cathode, 9 joules of energy will be released. So it's a set amount. It tells you the potential difference, and then how much energy is released depends on how many coulombs of charge make that transition. It's kind of like, this is a gravitational potential height difference between my two hands. Now how much energy is released depends on the weight of the thing that drops down. So if a marker is dropping down, less coulombs, in this case less mass, less energy is released. But if, for example, a large book or something, or a notebook drops, more energy is released. So in here as well, the more coulombs make that travel, more electrons make that travel, more energy is released. So this simply tells you the potential difference. So if you look at zinc, it's negative. So if I were to hook up a zinc half cell to this, then the electrons would be going the other way. They would go from the zinc half cell toward the hydrogen standard electrode, and so as a result, this would be minus 0.67. And if you use a voltmeter and you reverse the cathode and anode, you'll see it will be negative versus positive. So in this case, it will be negative 0.67, which means that the electrons are actually going from zinc toward the hydrogen electrode. So that's how they get those values. So they put 1 molar solutions of those guys, then they compare them to the standard hydrogen electrode. And so that's how they quantify the tendency of those species, whether they're molecules, ions, polyatomic ions, or elements, their tendencies to want to grab electrons. So next we are going to do an example, but the video is getting too long. So next up we are going to do an example where we put that formula to work and calculate the cell potential. Let's say I'm going to use a Daniell cell, which I introduced earlier. We're going to measure the cell potential using that table for a cell. So we'll do that next.